Welcome back, everyone. So now that we have discussed the class of models that we're interested in, let us define and discuss one of the main notions, not just of the semi-classical approach, but of this entire conference, in fact. And that's the notion of Fermi surface. So we have the best understanding of what a Fermi surface is in the simple situation that we have, where the system is purely periodic and not perturbed. So, for example, one example of a Fermi surface is on the conference poster. So that is one particular case of a Fermi surface where you can already see that the geometry and topology might play a role in the conduction properties, because these white lines here are supposed to be trajectories. So the Fermi surface can be derived from the band picture. So this was this here, what we derived in the previous section. And what you're seeing here is a collection of spectra of the fiber operator, of the periodic fiber operator. So this here the vertical slices, for example, this here, the collection of points would be the spectrum of the fiber operator at this particular value of Bloch momentum. As I've said, or I've stated, these energy bands are locally analytic. Also, their eigenfunctions, once you choose a suitable phase, can also be made locally analytic. So they all have very nice Taylor expansions. We can, we have very good control over what these functions look like. So, for example, isolated bands are therefore analytic. So let's get started with the actual definition of Fermi surface in this particular context. So the Fermi surface is a collection of points in the Brillouin torus. And of course, it is defined with respect to the Fermi energy, hence the name. So that there exists a band function at this point that intersects with the Fermi level. So let's just use this sketch here to actually get a better grasp of what it is. So in general, the Fermi level intersects with more than one band. So here you have points of intersections with the band E1. So just a reminder, since you sort bands by size, this is band E1, and this is band E2. And if you choose this Fermi level, then it has intersection points with band 1, so here and here, but it also has, and presumably here. And it also has intersection points with E2. So here and here. So that's very important. In general, you have more than one band contributing to the Fermi surface. But to simplify the discussion a little bit, let us consider this situation here, where we have an isolated band, so it's separated from all the other bands. Everything is, and the entire band E3 is analytic, so we don't, we don't have to pay attention to special points in a sense. And here the Fermi surface consists of 3 points. Again, this is a one-dimensional representation of a band picture that is d-dimensional. So this is just for illustrative purposes. But one thing that you can already see is that typically the Fermi surface has codimension 1. So this is, since you're dealing with a very regular function with a locally analytic function, unless your Fermi level just happens to be at a band intersection, it's the intersection points are just points where all of the band functions are locally analytic. So this is very good news, because you know that the Fermi surface will also inherit this regularity. So in general, what you expect is that the Fermi surface has codimension 1, so it's d minus 1 dimensional. If you're thinking of a three-dimensional sample, then usually that's why you say Fermi surface, because typically the Fermi surface is in fact something two-dimensional. And of course, for other dimensions, you just stick to this moniker simply because this was established already in the literature. So you say Fermi surface even if the dimension is different from 3. All right, so just to simplify the discussion a little bit, let me make the assumption that we're in the situation indicated in the figure. So, namely that the Fermi energy intersects only a single band that is isolated from the others in the sense that, just like in this picture here, E3 does not intersect with E4 or E2. So you can, in this case, you even have a global gap, but a local gap would suffice. So there is a positive distance between the band E3 and its neighbors below and above. That's what I would like. So this is simply to simplify the discussion a little bit. So one of the reasons why this is simplifying is that if you were to move the Fermi energy, let's say here, then for states that are localized, let's say here, the correct band function that you would have to use in the semi-classical equations would be E2, whereas here you would have to use E1. So this is a little bit annoying, and it's just simpler to instead just think of a single band. So because then what we can do, we can simply say, in this case, the Fermi surface is just a pre-image of band function 3 with respect to the Fermi energy. So really the Fermi energy picks out a single band. There's no confusion. Why is the Fermi surface so significant when we talk about conduction properties? I cannot spell. Significance. The reasoning is as follows. Electrons are fermions. So if we just set the temperature to 0 for simplicity, even when the temperature is non-zero and let's say at room temperature levels, this is the argument I'm going to make is still correct, just approximately correct, but to very, very high fidelity. What you will do is you will fill all states up to the Fermi energy, and that is because of the Pauli exclusion principle. So the physical state of the system will be just the so-called Fermi projection. So the Fermi projection is just defined using functional calculus. Since the operator is bounded from below, I can just include infinity here. And of course, the Fermi projection, after adjoining with a discrete Fourier transform or some version of that, also has a direct integral decomposition. Where Pf of k is a finite rank projection that consists of all the projections onto all the eigenspaces corresponding to all energy bands below the Fermi energy. Note that in a metal, the number of bands will actually change. So here, let's say if you're here, you have 1 and 2 energy bands below, whereas here you have 1, 2, and 3. So the rank of the projection is not constant. Nevertheless, this is a good projection. And when you bring the system out of equilibrium, you perturb the Fermi projection. You perturb the state of the system. And the only states that you can excite are those very close to the Fermi energy. Because bringing up a state, let's say, from here to here would require a lot more energy than bringing a state from here to here. Again, why is it necessary to push all the way to here? Well, that's because all the states here are full. So you cannot just make, let's say, a small a wave packet that moves from here to here. That's not allowed by the Fermi exclusion principle. So instead, what you would have to do is you would have to look at this state where you can excite, let's say, a wave packet that is just below the Fermi energy and then transport it just above. So these are the states that contribute to the conduction. And again, the physical principle that's behind it is the so-called Pauli exclusion principle. All right, so that should at least motivate roughly why the Fermi surface is important when studying conduction properties. One nice corollary is that if the Fermi surface is empty, meaning, let's say, let me erase the band E3. So in this case, the Fermi energy lies in a spectral gap, meaning there are no states here, there are no energy bands and no corresponding states, which means that if you choose a spectral projection around the Fermi energy that is smaller than the gap size, then this will be the operator 0. So in this sense, there are no states. And by what I just said, because there are no states that can be easily excited, this is an insulator. This does not conduct states. You could say, well, but I could still move states from here to here. That is correct, but the energy that is required in actual physical systems is so large that you would destroy the sample. So just think of an insulating material. If you increase the voltage enough, if you crank up the voltage, eventually, well, you can make it conduct, but maybe at the price of incinerating this insulator in the process. And if you look at it energetically, this is indeed what happens. So unless you're in a semiconductor, this is the spectral gap is of the order of electron volts, and that corresponds to roughly 10 to the 4, 10 to the 5 Kelvin. So basically you would destroy your sample. So now let us actually study what some examples of Fermi surfaces. So even when you have conducting states, the shape of the Fermi surface can be fundamentally different. And here I have 3 examples. So this here is a Brillouin zone. Just think of it as a torus that is unfolded. So to make it back into a torus, you would have to identify opposing sides. So for example, you would have to identify this surface with this surface, and likewise with the others. So if you switch them, if you do that, then you get a torus back. Or another thing that you could do is you could just glue on several copies at these surfaces. And okay, one claim is that knowing nothing about the materials, just looking at the Fermi surface, you can see that these 3 materials are essentially, or are expected to be essentially different from one another. So in the first case, the Fermi surface is like a sphere. So it's a bumpy sphere, but topologically speaking, it's a sphere. So importantly, it does not intersect with the boundary surfaces of my unfolded torus. And that means that if I were to tile with this Fermi surface, you would have no handles like you have here. But if you have an intersection, then, for example, this guy needs to be connected up with this guy. So you could actually move from one unit cell to the next. Whereas here, you would be confined to the surface of the sphere within one single unit cell. So that already gives you an indication that depending on the topology of the Fermi surface, you could expect very different conduction properties. And the reason for that is if you choose very simple semi-classical equations of motion, I will write them down in just a little bit, then the trajectories would be constrained to the Fermi surface in k-space. And that means here you already have a restriction to stay on the surface of, let's say, this approximate sphere. And there's no way to bridge from one unit cell into the next. So instead, the trajectories would have to go round and round and round. So you would only have closed orbits if you look at the projection in k-space. But here you would, what you would allow is basically trajectories that, depending on how you look at it, either cross here or they enter, let's say, from the left side, exit on the right side, and enter back onto the left side. So they would only go in one direction, whereas here they would have to continuously change direction, but once at one time they would point away from you, and another time they would point towards you. So the k vector necessarily would have to change sign, and you can already see that you would probably expect very different transport properties. So this is a very, very simple example. You can also think of a more complicated Fermi surface. So this is another example, I think, from a superconductor. And here you really see anisotropic behavior. That just means that the shape of the Fermi surface depends on the direction. So in this direction, so if you look at the red parts, you have something that is looks like a cylinder, but because you have to identify all these points, you would actually get a torus again. But importantly, the directionality of the I don't want to say infinite direction, but I think you understand what I'm getting at. So here you have a constrained direction. So here you would have to go in circles, but here you can really wander off from one boundary surface to the other. So you would anticipate very different conduction properties in this direction compared to the direction perpendicular to it. And likewise, if you focus on the blue bands, then you would have sort of very different behavior still. So the whole point is that it's not just the topology in the sense of the genus, but it is really the directionality of the shape that matters. So the question still is, so how do topology and geometry of the Fermi surface influence conduction properties? Of course, I'm being a bit intentionally vague here, because when I, for example, say geometry, there are many different kinds of geometries. And I believe that if you want to have a sufficiently general Fermi surface, the good type or one useful geometry to study would be symplectic geometry. but this is something I hope I will get to towards the end. So for now, just keep in mind that when I say topology and geometry, it is still not really clear what precisely I mean by that, and you would have to be a little bit more specific. So, but let's say this rough idea of research, this was kicked off by Lifshitz in the late 1950s. So, for example, there's a paper by Lifshitz, Abel, and Kaganov. And Abel and and Lifshitz and Peshansky. So this was a little bit later in 1959. The important point here is that they basically approached this from the point of view that they cannot solve the Schrödinger equation or the eigenvalue problem explicitly, and so they proposed a simplified semi-classical model, and the relevant equations are as follows. So R dot is equal to the k gradient of the relevant energy band function, and k dot is just the magnetic contribution to the Lorentz force. So importantly, there is no electric field. And this is relevant because the electric field, remember, is what is driving the current. But what you get in return is something quite powerful, namely that the energy is conserved. So a magnetic field does not change the energy. So En is conserved under the dynamics. And that has the nice consequence that the trajectory, or let's say the projection of the trajectory to this k-space coordinate is constrained to the Fermi surface. So this is extremely important because now you have a direct link between the topology of the Fermi surface to the behavior of a semi-classical system of motion. So now what you can do is you can just say, okay, you can classify trajectories, and this was done for very important contributions were done by students of Lifshitz and their descendants. So, for example, Novikov and Maltsev. So Alex Maltsev will give the plenary lecture, the introductory lecture to the topic in the workshop. They have contributed a lot. They are the works by Dunikov and by a few others. So the point is that this has been a subject of studies for literally decades, where people worked so consistently contributed to the idea that these trajectories are constrained and to the Fermi surface. And so you can think of, let's say, a more in-depth analysis of the types of trajectories that you might get. So one type of trajectory would be like the red one here. So this here is a closed trajectory. But there's also another nice trajectory here. So let's just pretend, for the sake of argument, that this is one side of the Brillouin torus, that is another. So you identify both sides here, and you identify these two sides, just for simplicity. And the green trajectory is an open regular trajectory. So clearly you would expect that the open regular trajectory makes a different contribution to the current than a closed trajectory. But you can also look at it even more closely and say that, okay, are there other types of trajectories that I should be interested in? And the answer is yes, chaotic trajectories. So here you see that the trajectory, it almost looks like a Brownian motion. Of course, I know it is not Brownian motion, but the point is that the length of the path is much longer than the distance going from here to here. So if you look at the green trajectory, the length of the path is almost as long as the geodesic in some sense. It's of comparable length. And here, the length of the path is obviously much longer than the length of the geodesic going from here to here. So in this sense, you would expect that chaotic trajectories have a much smaller, or will give a much smaller contribution to the current than open regular trajectories. And making these ideas precise, classifying the different types of trajectories, because one thing that you also have to keep in mind is you also have to look at, in some sense, how many open regular trajectories there are, how many chaotic trajectories there are. So you have to look at phase space and separate the different regions in phase space, and then average them up to get a total contribution to the current. But the point is that chaotic trajectories are expected to have a lower contribution to the overall current. at least intuitively speaking. Making this mathematically rigorous is, of course, a much more difficult proposition. To close this section, let me talk about some shortcomings. So even though a lot has been done, I think it is important to say that this is not a closed story by a long shot. And the reason, one of the reasons, it can be found in the semi-classical equations of motion. So let me just copy them. So the first important thing is that there's no electric field. And the reason is quite simple. If I add an electric field back, then the momentum component of the trajectory would leave or could leave the Fermi surface. So if the electric field is non-zero, then K of t is not an element of f EF is possible. Indeed, you would expect this. The second shortcoming is, of course, the system is not driven out of equilibrium. So the current that you might observe is not the actual current that is relevant, but the so-called persistent current. And when you do other approaches, say linear response theory, you usually subtract the persistent current. So even just adding an electric field means that the Fermi surface is no longer capable of encapsulating the basic properties. But there's also another very, very important fact, namely that these equations do not include subleading corrections. So let me just add this here. So the subleading corrections, so these are just what I call plus order epsilon terms here. They turn out to be crucial to understand certain types of insulators. So it's not even optional to include them, for otherwise you would get the wrong prediction. And if you look at the structure of these terms, it looks well, let's be careful and not say something that I cannot prove. But at the very least, it looks, it's not clear that the order epsilon corrections will not have any impact on the conductivity. And if you look at the order epsilon corrected trajectories, so k epsilon of t, that's just the momentum variable in the epsilon dependent flow. So I'm just including the order epsilon terms in the semi-classical equations. And I'm transporting momentum using the epsilon corrected flow. Then also here, you would expect, or at least it's not clear whether or not the k variable, the momentum coordinate, will stay on this on the Fermi surface. So in general, this will be false. So the trajectory is no longer constrained to the Fermi surface, and so you would have to do some extra work to connect the Fermi surface to properties of this dynamical system. But let's say on a larger scale, I would actually say the problem is even deeper. So the actual problem is that when you're talking about trajectories, then you should talk about phase space. And the Fermi surface, the way it's defined, is not an element of phase space, which in this case is the cotangent bundle to the Brillouin torus. Sorry for this T star here. But this here is phase space. And it would be much more natural to talk about phase space when you think of trajectories being constrained or not constrained on certain surfaces. So this is really something that requires another look. And I would say that the solution to go forward is to define the Fermi surface, and the epsilon should just indicate it's for the epsilon corrected equations of motion. As a subspace. So, and it should inherit the symplectic structure. So that it is left invariant by the epsilon corrected semi-classical flow. Because then you can really connect the properties, the geometry, the symplectic geometry, or perhaps some notion of topology of the Fermi surface with properties of the trajectories. So you can use this constraining idea. All right, so that's it for section 2. Next up, we will talk about semi-classical approximations.